Welcome into this video on related rates for volume. We also have some related rates involving area, and we're going to, in this video, I'm going to talk to you about what we mean when we say the term related rates. Okay. If you hear what sounds like rain in the background, it's a little bit of rain from one of the hurricanes that come in this time of year. But I'm okay, and I'm going to teach you some math in this video. So let's take a look here. Related rates. All right, so we're going to solve some related rate problems involving area. We have some involving volume, and that you'll see those in the Newton assignments. Let's take a look at this slide just briefly here. There's some real-world context where the quantities, like with length and width, right, are related, and they give us this formula for area. Okay, so think about this example. We have a balloon with radius r and a volume of v. The rate of change of the volume is related to the rate of change of the radius. Okay, and we know that because of that formula for the volume of a sphere. Okay, so the volume of a sphere is, I think, 4/3 pi times the radius cubed. Okay, so we're going to look at one of those in just a second. The idea is, if we start out with the smaller, so you can imagine you're looking at a balloon here. Here's the radius of that balloon. As the volume of the balloon increases, so does the radius. Okay, and if I were to draw really good circles, you could see that a little better. But what we want to be able to do is relate how fast the volume is changing with how fast the radius is changing. There are some steps here that are going to involve that you can use as you go throughout these problems. One thing to remember, we say right here, use the chain rule, differentiate both sides. We're not always going to use the chain rule. Sometimes we'll be using the product rule. It just depends on what the application is that we're looking at. Oftentimes, though, there are going to be some known values that we can substitute in to make our equations a little easier to look at. Let's take a look at this one. So we have a giant ice cube. Okay, now this is crucial. It's an ice cube, right, which gives us this shape. And my drawings aren't going to be really great, but we'll manage. So we have that ice cube, and it looks like this, right, or something like this. So the idea is the volume of this cube is whatever the side measurement is cubed, right? So when we talk about the volume, generally talk about length times width times height, but in a cube, all of these are the same. So we're gonna be working with this formula right here. Now, the Newton slides here use V of t and S of t, and what they're really saying is that the volume and the side measurement are changing as functions of time. You can make this a little simpler if you just look at it in terms of this, V equals S cubed, okay? Now there are a couple of things to note right here. One of the things is that the volume of the ice cube decreases at a rate of 8 cubic meters per second. So if we were to go in and identify what our knowns and unknowns are, right, we've got dV dt equal to -8, okay? Now, as we go throughout this problem, there are going to be some knowns and unknowns that we want to use at particular times. So let's go back and look at this. What I want to know is what is an equation for dV dt, right? So I'm going to take the derivative of both sides, and I'm taking that derivative with respect to time. So let's talk about that just briefly. This says that the volume is decreasing at a rate of 8 cubic meters per second. So because it says per second, we know that we're going to take the derivative with respect to time, right, dt. So that's what we have here, right? So dV dt is going to be -8, and that's going to equal 3 times the side squared. Now notice it says find the rate at which the side of the ice cube changes when the side of the cube has a length of 2 meters. Okay, so basically at that moment in time, when S is equal to 2. Now the thing about it is we don't go ahead and plug that 2 in at the beginning. We don't plug 2 in right here because that side of that cube isn't always going to be 2, right? The length of the side is changing, and that's why we wait until after we get the dV/dt to plug in the 2 for our side measurement. So if we simplify that, right, 3 times 2 is 6, and negative 8 over 6, let's see. Sorry, I didn't square my 2. Pardon me, I left that out. 2 squared is 4. 4 times 3 is 12. So our ds dt, much like what the Newton slide here has, is negative 8 over 12. I might reduce this to negative 3/4 ds dt, right? Excuse me. I got a little carried away with my ds dt. I might reduce this to negative 3/4, right? So we're going to take this value, move it to the other side, and isolate ds dt. So again, we talk about when should we plug those numbers into our equation, and how should that look, right? So what I want you to notice is in this problem we have a trough with the ends shaped like isosceles triangles. The width of our trough is 3 meters, okay? The height of our trough is 4 meters, and we have a length of 8 meters. Now think about this. The width here, let me adjust my pen. The width of the water changes as the height changes, okay? And there's a relationship between the height and the width. The width is 3/4 of the height. Now you may look at this and think, well, how did I know to do that? How did I know that was something I need to keep in mind? When we talk about this right here, water is being pumped into the trough at a rate of 3 cubic meters. So what we know is that the volume is changing at a rate of 3 cubic meters per minute. Okay. What rate does the height of the water change? Now, this is your clue. You're looking for dH dt. Okay. But if you think about the formula for volume, now this is the volume of a rectangular prism, so it's going to be 1/2 the length times the width times the height. When you think about this thing, you have to be aware that if I'm taking the derivative with respect to time, not only would I have a dV dt, I should have a dL dt and a dW dt and a dH dt. We can avoid those, okay? So I don't need the dL dt and I don't need the dW dt if I take some things into account right here to begin with. First, taking into account that the width is 3/4 the height. So where did that come from? Well, the width is 3 and the height is 4, and that ratio is always going to hold true for this situation. If we take that into account, well, now we also know that the length of our prism is not going to change, right? The length from here to here is always 8. It doesn't matter what the height of our water is. So in that case, the length is 8, and the dL dt is 0, right? That length is not changing. Well, now we have some things that we can go ahead and plug in. Okay, so we said that we knew that the volume was equal to 1/2 the length. Well, the length is going to be 8, and it's always 8. The width is going to be 3/4 of whatever the height is, and then we're multiplying by the height. Now you'll notice we say, at what rate does the height of the water change when the water is 3 meters deep? In other words, we want to know what is dH dt when h is equal to 1. So there are some clues about some things that we're going to plug in. Now that we have that equation, V equals 1/2 of 8 is 4. Those 4's cancel. So our V, our volume, is just 3 times the square of H. Well, we can look at how Newton does this, right? So we take dV dt. I'm going to take the derivative of both sides, and I'm taking the derivative of 3h squared. That's going to be 6h dH dt. in our problem, we said that the volume is changing at 3 cubic meters per minute. So I can plug 3 in for dV dt. We wanted to know dH dt when the height was 1 meter. Well, I'm going to divide both sides by 6, and that gives me 1/2. So I know that dH dt is 1/2 meters per minute. Now we do have a little bit more of an in-depth discussion right here in the PowerPoint slide, so you can go back and look at that on your own time. If you have some questions, obviously you reach out. I'll be glad to help. There's one more type of problem I want to look here, and it involves the radius of this circle. Okay, so we have the radius of a circle increasing at a rate of 4 meters per second. Now notice we don't give you, in the problem, we don't give you any formulas to work with. We tell you that the radius of a circle increases at this rate. Find the rate at which the area of the circle is increasing. If you go back and look at your steps, right? Assign symbols, state in terms the information that's given, and find an equation relating the variables. Okay, so in this case, the equation we're going to focus on is the area of a circle. I like to do it in a little bit of a different form. I like to identify the area or the formula that relates these values first. And now that I know that we're looking at A and R, I know that I need to find DAT in my problem, DADT in my problem. And the rate at which the area is increasing when the radius is 6, that's what we're looking for, is find the rate at which the area is increasing. I know R is going to equal 6, and I also know that dr dt is 4 meters per second. Well, with this information, I can come down here and find my area formula, right? The dAdt formula. dAdt is going to equal 2 pi r dr dt, right? No special chain rule or product rule right here. So 2 pi r dr dt. We do know from the problem that we're looking for dAdt. That's the information we want to find. And I'm going to have 2 pi times the radius at this particular point in time. I want to know what is the rate at which the area changes when the radius is 6. And I know that the radius of the circle increases at this rate, 4 meters per second. So we're going to go 2 times 6 is 12, 12 times 4 is 48. So the area of the circle is changing at 48 pi square meters per second. This is one that you're going to see at the very beginning of your Newton problems today. I think this is one of the first problems right out of the gate. Notice that we're talking about a rectangle has a length that is increasing at this rate. So that is going to be dl dt. What is the rate of change of the area of the rectangle? So we know that we're looking at the area of a rectangle, A equals LW. But here's some important information that you don't want to look over. The width is being held constant. That's just a fancy way of saying dw dt is equal to 0. So look what happens when we find out what dA dt is. If I take the derivative of this, dA dt, it's equal to 1 d2 plus 2 d1. Now, when you look at this problem, you'll notice they didn't give you any information about the length. They did, though, tell you that dw dt was 0, so this thing just goes away. It just goes to 0. I want to know the rate of change of the area, right? What is the rate of change of the area? So I'm going to have dA dt equal to W, the width is 8 inches, so 8 times 2 dl dt, right? The width at which the rate at which the length is changing. This is where we're getting 16 square meters or 16 square inches per meter. So for the next step, you do have some problems in Newton that you need to take a look at. Make sure you're going through those, you're taking your time. I say this in every video, and I mean it every time. Reach out to me. I can make you custom videos. I just need to know what problems you're having, and I can post those to the Canvas course shell.